Modern computing and telecommunications are reaching the thermal limits of copper. Pushing electrons through traditional metallic pathways at higher speeds generates intense, unmanageable heat. Beyond the heat, copper suffers from inherent signal loss and strict bandwidth caps that prevent efficient data transmission over long distances. The Photonic Integrated Circuit, or PIC, bypasses these limits by operating with photons. As this diagram shows, electrical signals are converted into pulses of light, routed through the chip, and then translated back into electricity at the output. This architecture allows both optical and electronic components to exist on a single semiconductor substrate. To understand how a PIC functions, we must reverse engineer its layout and isolate the specific quantum interactions used to generate, manipulate, and detect light. PICs represent a transition from merely pushing electrons to mastering the bidirectional bridge across semiconductor bandgaps. We begin at the first critical block on the PIC, the light source. For high-density data transmission, the system requires a stable single-mode source. This energy band diagram illustrates the underlying quantum mechanism. Electrical pumping forces electrons into the conduction band, achieving a state of population inversion, where excited electrons outnumber those in the lower energy valence band. In this state, an incoming photon can force an excited electron down to the valence band, triggering stimulated emission. This releases a second photon with the exact same phase and direction as the first. This process is distinct from simple LEDs, where spontaneous emission creates a broad, unusable spectral width. However, basic Fabry-Perot laser cavities are still too noisy for integrated circuits because their dual mirror design allows for multiple unwanted modes of light. PICs solve this using the distributed feedback, or DFB, laser diode. Notice the corrugated grating structure built into the active region. This periodic grating acts as a filter, providing optical feedback that amplifies one specific, highly stable wavelength. The DFB laser essentially organizes random quantum emissions into the strict coherence required for on-chip communication. Once emitted, the coherent light beam enters the next block, the waveguide. This waveguide relies on total internal reflection. By using a core with a higher refractive index than the surrounding cladding, the light is trapped and guided along the path with minimal leakage. Even with high-quality materials, the signal eventually attenuates, losing strength as it travels. To counter this, the chip utilizes a semiconductor optical amplifier, or SOA. While long-distance fiber cables use bulky erbium-doped fiber amplifiers, the SOA is compact enough to be fabricated directly onto the semiconductor chip. The SOA uses electrical current to create its own population inversion. When a weak optical signal enters the block, it triggers stimulated emission, exited with significantly higher amplitude. Because this happens purely in the optical domain, the signal is boosted without the heat or latency associated with electronic conversion. The final block of the PIC is the photodetector. To be processed by standard hardware, the pulses of light must be translated back into readable electrical signals. This relies on the photoelectric effect. In this PN junction, incoming photons strike the valence band with enough energy to eject electrons into the conduction band. This impact creates an electron-hole pair. The built-in electric field of the PN junction immediately separates these carriers, pulling electrons toward the N-type region and holes toward the P-type region. This continuous separation of charge generates the final electrical current. The efficiency of this stage is defined by its responsivity, the amount of current produced per unit of light, and its quantum efficiency. The photodetector acts as the functional mirror to the laser diode, completing the bidirectional translation between light and electricity. Viewing the entire integrated circuit reveals the most significant hurdle in manufacturing, the physical boundaries between incompatible materials. Silicon is ideal for routing light through waveguides, but its indirect bandgap makes it an extremely poor light emitter. For light generation and amplification, engineers must instead use 3V semiconductors like indium phosphide. This requires hybrid integration, the process of bonding these 3V materials directly onto a silicon photonics platform. This creates physical stress due to a disparity in thermal expansion coefficients. The materials expand at different rates, which can warp the chip. Furthermore, the different crystalline lattice structures of silicon and indium phosphide make microscopic bonding difficult to achieve. Overcoming these hybrid integration challenges is necessary to scale optoelectronics for mass deployment. The result is a complete high-speed data flow, converting electricity to light, routing and amplifying it, and then translating it back to electricity. This system relies entirely on our ability to manipulate the semiconductor bandgap. Scaling these systems further depends on the adoption of quantum dots. Quantum dots are semiconductor nanocrystals between 1 and 10 nanometers. Here, quantum confinement replaces continuous energy bands with discrete quantized levels. Engineers tune the emission wavelength simply by changing the nanocrystal size. Smaller dots emit blue light, while larger dots emit red. As materials science overcomes the hurdles of hybrid integration and implements nanoscale structures like quantum dots, optoelectronic circuits will replace traditional microelectronics at the core of global computing infrastructure.